All right. Um, in this video, we're going to solve a uh, adiabatic PFR that is carrying out multiple reactions. So basically, we're going to modify the Python solution that we've been using to account for multiple reactions and heat effects. Okay, so, and this is the wrong page, so here we are. Okay, so this says the gas phase elementary reactions 2A goes back and forth to B and 2B plus A goes to C are carried out adiabatically in a PFR with no pressure drop. Plot the temperature and concentrations along the volume of the PFR, and we're given some information. So I'm going to set this problem up and then show you how to solve it in Python. So the first thing I want to do, these are elementary reactions, and we aren't given rate laws, so I want to write those down. So I'll say reactions and rate laws. So we have reaction 1 is going to be 2A goes back and forth to B, and the rate law there is minus RA is equal to K1A times CA squared minus CB over KC. And then reaction 2 is going to be 2B plus A goes to C, and the rate law R2C is going to be equal to K2C times CB squared times CA. And I'm going to write the second reaction in terms of species C because that's what the rate constant is. The rate constant for that reaction is given in terms of species C. And you don't have to do it that way. That just helps me with when I write out the problem, it helps me with the accounting and keeping track of the different species. Okay, so now I'm going to rewrite these reactions for the stoichiometry matrix, and this is going to take a couple of steps, which we'll walk through. So I'm going to rewrite the reactions for the stoichiometry matrix. Two things I'm going to accomplish here. Number one, I'm going to scale the stoichiometry of all the different reactions so that the stoichiometry or the stoichiometric coefficient on the species with which the rate is written in terms of is equal to 1. So that means for reaction 1, I'm going to divide everything by 2 so that the stoichiometric coefficient on A is equal to 1. And for reaction 2, I don't have to do anything there. The rate there is written in terms of species C, and the stoichiometric coefficient on species C is already equal to 1. Okay, so we're used to doing that. The other thing I'm going to do, since reaction 1 is a reversible reaction, I'm going to actually break that into 2 reactions, and that's going to help me with my stoichiometry matrix. So I'm going to rewrite and renumber these. I'm going to write reaction 1 is going to be the forward of what used to be reaction 1. Reaction 2 is going to be the reverse of that. This is a new reaction 2. And then I'm going to write what used to be reaction 3, what used to be reaction 2 is now reaction 3. And that is going to, isn't going to change. So 2 things I did here. I split reaction 1 into 2 reactions, a forward and a reverse, separately. And then I also divided the stoichiometric coefficients on what is now reactions 1 and 2 by the stoichiometric coefficient on A, because the reaction is written in terms of A, and we need that to be 1. Okay, now I'm going to rewrite the rates of these. I've scaled the stoichiometry. The rate laws do not change, so they're going to remain what they were. So reaction 1 is going to be maintain the same order of reaction, but I'm only going to write the forward reaction. So I'm going to say CA squared. So I'm not going to take that CA squared and turn it into CA. I changed the stoichiometric coefficient. That does not mean I changed the kinetics. But what I am going to do is, since I'm now only talking about the forward reaction, I'm only going to write the rate of the forward reaction. Similarly, for reaction 2, I'm still going to write that in terms of species A. Now I have a rate of formation of A because A here is a product, and I'm only going to take the reverse reaction from what was originally reaction 1 in this new reaction 2. So the terminology is starting to get complicated here. But this is, if I write this out, this is the reverse reaction of what was formerly reaction 1. And so now that I've expanded this into 2, I'm going to write this out as a forward reaction, and I'm going to maintain the same kinetics. Okay, so now reaction 3 is going to keep the same rate law. I'm just going to re-index my numbers to be consistent with my new reaction numbers. Okay, now I'm going to write the stoichiometry matrix. And we're used to doing this now that I have my new reactions. And then I can also write my rate matrix. And so now I have the information that I need to put into Python. So I'll go over there next. All right, so here I have the Python solution for the multiple reactions in an adiabatic PFR problem. Okay, so I'm going to start out here by entering or by loading up the functions that I need. I'm always going to bring in this numpy. I'm going to bring in ODE int because I'm solving a PFR, so I need a ODE solver. I'm going to bring in my plotting function because I want to plot the results. I'm also going to bring in this math function. This is going to allow me to use exponentials, which I need for my Arrhenius and Van 't Hoff equations, and I'll show you that in just a second. When I load up my given information, I have to load up my non-isothermal pieces, so my heat capacities. I have my reaction thermodynamics. One thing to note here, so we said that the heat of reaction 1 is minus 20 in the original problem. We broke reactions 1 and 2, we broke reaction 1 into 2 reactions, a forward and a reverse. So reaction 1 is the forward reaction, reaction 2 is the reverse reaction. They're going to have the same heat of reaction. It's the same reaction, except it's going to be the negative of each other. So if A goes to B is, A goes to 1/2 B is minus 20 kilojoules per mole, then 1/2 B goes to A is 20 kilojoules per mole. One thing that I forgot to show you on the last, in the OneNote file, I want to write, I'm given my heat of reaction for my third reaction, what was originally my second reaction, but is now my third because I rewrote them. I'm given that in terms of moles of species B, but I'm given my rate information for this reaction in terms of species C. So I want to make those two things consistent. So I used stoichiometry to say if I have 2 moles of B for every 1 mole of C, then I would need to multiply the heat of reaction in terms of species B by 2 in order to get the same quantity in terms of species C. So that's what I've done here. And you can show this by writing out the units explicitly. Now I'm going to load in my reaction kinetics. I need to do this because, I need my rate constants to begin with, but I also need to know the temperature dependent quantities, or the quantities that will help me write the temperature dependence for them. So I'm given values. This is my rate constant for reaction 1. This is my equilibrium constant for reaction 1. So these will be used in my reactions, my new reactions 1 and 2. I'm given, this is the temperature for the equilibrium constant. I'm using this notation just to kind of remind myself. So if I'm calling this KCA, I'm saying that this is TKCA. Another thing to note here, I've added these zeros here. These are my initial values for all of these quantities. And I'll show you why I'm doing that in just a second. This is my rate constant for reaction 3, and then I have my activation energy for reaction 1 and my activation energy for reaction 3, along with the temperatures that those, or that the rate constants, that those particular rate constants are defined at. Okay, my reactor is going to be very small, 1 liter. My feed information, I'm given that here. I have to supply an initial temperature because this is a non-isothermal PFR. I'm told it's 150 C, so I'm just going to add the 273.15 to that to get Kelvin. I enter in my stoichiometry matrix. We're used to doing that. And I'm also going to set up my initial conditions. So I'm going to set up, normally what I would do is have a vector here of 3 values, one for the inlet molar flow rates of A, B, and C. But I also have this temperature term, so I have to expand this by 1 entry in order to supply my initial temperature. Okay, so now I'm gonna combine some of this stuff together so I can feed it to my function. I'm gonna end up having a pretty complicated function, or a function that requires a lot of variables now. So doing this just kind of neatens it up. I'm gonna take an initial concentration matrix. Basically, what I do there is I'm gonna sum all the initial concentrations to get my total initial concentration, which I'm gonna need for my concentration equations. I'll show you that in just a second. And then I'm going to need my initial molar flow rate matrix or vector, and that's going to be my part of my initial conditions. Actually, I don't think I actually end up needing that because I specified that here. Another thing I'm going to do just to simplify some things as I'm going to load the heats of reaction as well as the heat capacities into vectors. And that way I can do some matrix math in the function below, and that way the more I can have the code do, and I don't have to do, the more likely that it is that I'm not going to make errors. So the code's less likely to make errors than I am. Okay, so now I'm going to define my PFR function. So we always start out by saying we have some variable, and I'm going to call it x. We can call it whatever we want. And then since this is a PFR with ODE in, I'm going to need to specify this, the integrate, the independent variable, which is the values that we're going to integrate over. Then I need to specify all of the values from the given information that I'm going to feed to my function. So the key here is just to make sure that you're bringing these, whatever order that the order at which you list them here doesn't matter as long as you're consistent every time that you call up this function. All right, so now I'm going to go in here and start defining my variables. I have my x variable. I'm going to say that's different columns. It's going to give me my flow rates of my different species as well as my temperature. Those are variables I'm going to use throughout the solution. I also need to define a total molar flow rate, which I need for my concentration equations. That's going to be equal to the flow rates, or the sum of the flow rates of A, B, and C. Next, I have my concentration equations. This says pressure. You can ignore that. That's just a typo. This is a gas phase reaction with a changing volumetric flow rate. We hence need concentration equations for all the species that are involved in rate laws. That's all of them. And the form I'm going to use is this CT naught times the mole fraction of the species at whatever volume, PFR volume we're at. And since this is a non-isothermal reaction, I also have to scale by this temperature term. So these are my concentration equations for this non-isothermal PFR. Next, I need to specify my thermodynamic and kinetic quantities, or my temperature-dependent thermodynamic and kinetic quantities. That's going to be my rate constants, K1A, K3C, as well as my equilibrium constant for what's going to ultimately play out in the rate constant for reaction 2. I'm going to use this mathexp form to do that, this mathexp syntax to do that. You see here why I, in my given information, called these values with a 0, because that way here in the function I can call them without the 0. That just kind of helps me see what's going on. These are just my Arrhenius forms of all of my different things. One thing to note here is I did bring in heats of reaction as a vector, but I also brought in this quantity for reaction 1 because I knew I needed that for my Arrhenius equation. Next are my reaction rates, so just typing those out. We've done this before, noting that here I have my reaction 1, reaction 2, that these are forward and reverse versions of the same reaction, but we've broken them into 2 separate reactions. My rate equation, or my rate vector, is then going to be my rate of reaction 1, 2, 3, and then I can dot that against the transpose of the stoichiometric matrix to get my net rates. My net rates are going to be, those are going to form the mole balances for my different species, A, B, and C. I'm going to use this item command to do that. What that's going to do is give me a scalar quantity rather than a vector. The ODE int solver is going to expect a scalar, so the more I can get rid of vector things now, or I guess I should call it array things now that I no longer need them. I use them here, for example, to make sure, because I trust this, simpler code and Python to do that multiplication / addition better than I will. But once I do that, I no longer need those things, so I'm going to start stripping it away. I can additionally use the matrices that I sent in to calculate my heat generated term. So that's going to be my heat of reaction times my rate. So I can, basically do that. As I do that, I'm going to take my the transpose of my rate matrix. I'm going to flatten that matrix. I'm going to flatten that matrix in order to remove the array character. And again, that's because I don't want array character in my what gets returned to the code. And the reason for that is because ODE int isn't going to want that. All right, similar, I'm going to do that with my heat capacity terms. So I'm going to take my flow rates, I put those temporarily into a vector and dot that against my heat capacities. That should give me my total heat capacity term. And then I can use that to sum up my energy balance. The nice thing about that is I get a pretty simple expression for my energy balance. Finally, now normally if I was doing a non-isothermal PFR, I would just need to return the net rates, because the DFDV terms are equal to the net rates. But now I have a non-isothermal PFR, so I also have this energy balance. So I'm going to create instead this variable called balance equations, which combines the mole balances and the energy balance. So again, I have 1, 2, 3, 4 entries. I also have 1, 2, 3, 4 species up here. I'm going to return that, and then I'm going to put it into the ODE int. I'm going to call ODE int to solve it. It's going to work on PFR with my initial conditions for flow rate and temperature along this PFR volume that I've specified. And I'm going to take my different arguments here, and this is basically a copy and paste of everything beyond the PFR vol argument here. And I'm copy that and paste that so that it's all in the same order. Once I do that, I can extract out the information. I've called this sol. You can call it whatever you want. Normally I call it F, but since there's a temperature there, I thought that was a little misleading, so I just called it sol. I can extract the different quantities that I want from the different columns here. So this here tells me that I'm going to take all of the values in column 0, all of the values in column 1, etc. I can then use that to write my total molar flow rate, which I can then use to write my concentrations. As you can see here, I forgot my temperature dependent terms down here, so I'm going to add those in. And then I can plot the solution. So if I push play here, cross my fingers, I get an answer. What we see is I start out at a pretty hot temperature. I drop down. That's because there's a lot of endothermic reactions going in there, bringing out temperature. I get some conversion of A, but not much over the course of the reactor volume. And I'm forming B more so than C. Probably if I extended this reactor volume out, I might see some more C. We can actually try that. Maybe if I went to 10 liters, maybe 100 liters, I don't know. Yeah, so there we go. If I plot out a little bit longer, I start to see more conversion. I start to see more C being formed. So that is what I have for this solution.